Hello all. Today I'm going to show you some of the limit and continuity problems that we're going to learn in section 13.2. We have talked a little bit about limit and continuity before in our class, and I told you what is the major concern when you are trying to understand limits and continuity in several variable functions. So for example, the example you are seeing on your screen is limit x comma y goes to 0 comma 0. So you have the point 0 comma 0 being approached, and as I have said, you can approach this point 0 comma 0 in so many directions, uncountably infinitely many directions. So if in all possible directions the value of the limit is the same number for a given function, then we say the limit exists. So what I'm going to show, first, let us try to approach the point 0 comma 0 on the x-axis. So I will say x comma y, my point, is approaching the point 0 comma 0, but it is doing it along the x-axis. And in the positive side, say, and I'm just going to throw it in. So you can approach 0 comma 0, the origin along the x-axis from the positive direction or the negative direction. So I'm going to say that in the positive side of x-axis. So I'm approaching from right, the point 0 comma 0. What happens? Well, think about your Cartesian coordinate system of 2 dimension. If you're approaching the point, the origin 0 comma 0 from the right on the x-axis, then the points are of the form x comma 0. So what it does, it translates the concept of the point xy going to the point 0 comma 0 to x approaching 0, because your y is always 0. Y is actually equal to 0. Whereas x is approaching 0, so x is not equal to 0. X is approaching 0, it is getting closer and closer to the value 0, so it is not equal to 0. So what we get in this situation? Well, I'm going to change the given limit, which was limit x comma y approaching 0 comma 0 for the function, and my function was x squared minus y squared over x squared plus y squared, and the entire thing was squared. That's what I'm trying to find the limit for. So I'm going to rewrite this limit in the previous context of approaching 0, 0 on the x-axis from the right-hand side as limit x approaching 0. And wherever I see y, I'm going to just replace that by the value of y, which is y equal to 0. So your function becomes x squared over x squared whole square. Now remember, your x being approaching 0, it is not equal to 0. So x squared and x squared, they're non-zero quantities, so you can cancel them. And this limit becomes limit x approaching 0. And as you can recall, 1 squared, which has nothing to do with x, hence the limit is going to be 1. I got x squared and x squared canceling each other, giving me 1, and then 1 squared is 1. So on the x-axis, I get the value 1. And as you can imagine, on the negative x-axis, I will get 1 as well. So what happens when I'm approaching the point 0 comma 0, but this time I'm doing, say, on the positive direction of the y-axis. So I say x comma y, it is approaching the point 0 comma 0, but this is doing on the positive side of the y-axis. Side of the y-axis. Then what I'm going to see? Well, it is pretty similar. You are approaching the point 0 comma 0 from above. So this is your way of approach. And think about any point on this is going to be of the form 0 comma some y. So your xy going to 0 has reduced to y is approaching 0. And because I'm approaching from above, I can say 0 plus, whichever way I want to write it. So what happens to my limit? My original limit x comma y approaching 0 comma 0, and your function was x squared minus y squared all over x squared plus y squared whole to the power 2. So I will do the same thing. I will just say that this now becomes limit. If you want to write, you can write y approaching 0, or to be on the safe side, just say limit y approaching 0 plus, and put x equal to 0. So you get minus y squared over y squared whole to the power 2. And again, y being not equal to 0, remember at this point y is not equal to 0, it is approaching 0. You can cancel the y square, they're non-zero quantities, and you get limit y approaching 0 plus, and I will get negative 1 whole to the power 2, which is a positive 1. So I get a positive 1 in both ways. So what I want you to understand right here, in both situations I got positive 1. But what if I did not have the square outside? So I have a square here. What if I did not have that? Then I do not have this square. I do not have this square. I still get 1 in this situation. But now let's go back and think about when you were approaching the point 0, 0 on the positive direction of the y-axis. Then you do not have this 2. You do not have this 2. You do not have this 2. So you are going to get a negative 1. So I have already given you one example where depending on which way you are approaching the point 0, 0, I have two different values for the limit. And hence I said that the total limit for this function as xy approaches 0, 0 doesn't exist. Well, but that was not our problem, so let's forget about what I said about not having the square. And then what we're going to try to understand, is there any other way or any other possible direction that we can think of where it's going to give us a different limit? So let's try to see that. So what if this time you are approaching the point 0, 0, but this time I'm approaching it along the y equal to x line. So say this is my approach. So what I'm going to now say, I can say that since y is equal to x and I am as a point x, y approaching the point 0, 0, neither y and hence nor x is equal to 0. So y is not equal to 0, x is not equal to 0. Remember, they are equal to each other though. So what I will do, I will rewrite my limit in one variable. I know that the function was limit xy approaching 0, 0, x squared minus y squared all over x squared plus y squared, and then I had whole to the power 2. And I'm going to rewrite this thing as limit x, y approaching the point 0, 0. And in my function, I'm going to go ahead and write x squared minus x squared all over x squared plus x squared. And I get to do that because x is equal to y. And instead of writing both x and y going to 0, 0, I can now rewrite this thing as limit x approaching 0 because I have only one variable here. And see what I get, 0 over 2x squared. Remember, x is not equal to 0, so the bottom is non-zero, whole to the power 2, and this is equal to 0. So problem, why? Because now you are approaching the point 0, 0 along the line y equal to x, and you get the limit 0. Whereas on x-axis and y-axis, both of them, I got the limit 1. So I have different limits in different directions. Hence, I get to say that. Thus, the total limit in this situation does not exist. The directional limit exists. In certain direction, you get a value for your limit, but the total limit does not exist. And how do I conclude that? Because I found two different directions. One is y equal to x, giving me a value of limit which is 0, which is not agreeing with the value of limit when I approach the point 0, 0 along the direction, say y-axis, and I got a value of 1. Those values are different, so the limit doesn't exist. So this is a problem. As you can imagine, there are so many different functions that you can think of in two variables. How to know which direction should you approach the limiting point and hence get to say whether the limit exists or doesn't exist. So what I'm going to show you for the rest of the lecture is some other ways to answer the similar set of questions and kind of avoiding this tricky path of finding a proper direction. we will primarily rely on the techniques that we have seen in Calculus 1 to find the limits. So let's go ahead and do some examples. As usual, when you are finding limit, your first try is going to be to see whether you can directly substitute values. So look at my example now. I'm finding limit xy approaching 3, 4, e to the power xy, several variable function. My question is, can I find the limit by direct substitution? Is there any problem? So let's see that. I will say limit x, y approaching the point 3, 4 of the function e to the power xy. So if you put in x equal to 3 and y equal to 4, direct substitution, you get 3 times 4, which is e to the power 12. And there is no problem doing so. So I'll go ahead and say that this is e to the power 12. Then it is asking me to discuss the continuity of the function, and it has 5 different options. Well, it is an exponential function, and as you can think of, the input values depend on both x and y, but it's still an exponential function, which if you think of the graph of the exponential function, it is continuous everywhere. It doesn't matter what is the input, it is continuous everywhere. So what I'm going to say, I will say that this function is continuous everywhere. Instead of saying that it is continuous over negative infinity and infinity, I will say it is continuous everywhere on R2, the two-dimensional Cartesian coordinate plane, because my inputs are points. They're no longer points on the line, they're points on the plane. So it is continuous everywhere. Pretty simple example. Let's try to see the next one. So this one, if you forget that whatever hint I have given you, if you look at this function, this is x squared minus y squared over square root of x squared plus y squared. Now, I am approaching the point 0, 0. So if I do direct substitution, I have a problem because I will get 0 square minus 0 square over square root of 0 square plus 0 square. So it is 0 over 0, and I can't do that. So generally for these problems, as you have seen, the example I was doing, I will try to go find different directions, but there is a marvelous way to solve these problems by transforming your entire coordinate system to polar coordinate system. So the hint says that substitute x equal to r cosine theta, y equal to r sine theta. So let's see what it does tell. So say x is equal to r cosine theta, that's my substitution. Remember, x is approaching 0, so r cosine theta approaches 0, which has twofold answers. It can mean that r is approaching 0 and cosine theta is approaching 0. Either r is approaching 0 or cosine theta is approaching 0. So think about cosine theta approaching 0. If cosine theta is approaching 0, then theta is approaching pi over 2. What else we know? We know the other substitution, and that is y is equal to r sine theta. And according to the limit, y approaches 0, which means r sine theta will approach 0 as well. So again, I have twofold answers. I have either r approaching 0 or I have sine theta approaching 0. Remember, theta was approaching pi over 2. Then sine of theta will approach sine of pi over 2, which I know is 1. That does not match the concept of sine theta approaching 0. What does that tell me? That tells me, well, this situation can't happen. Cosine theta cannot go to 0. So if cosine theta is not going to 0, I will say definitely r is approaching 0, and I will forget about this side. At least r is approaching 0. And that's exactly what I told you here. And note that if xy approaches 0, that implies r must go to 0. So in terms of this substitution, I have to rewrite the given functions and the limit. So let's try to do that. So you have limit x comma y approaching the point 0 comma 0. And your function was x squared minus y squared all over square root of x squared plus y squared. So replace x by cosine theta, y by sine theta, of course r, and the limiting value, you say limit r goes to 0. X squared is r squared cosine square theta. Y squared is r squared sine square theta. And that is sitting over square root of r squared cosine square theta plus r squared sine square theta. As you can possibly see now, the bottom is going to be so beautiful looking. I will say that this is limit. What I will do, I will factor out the r squared from top and bottom. So I will get r squared times cosine square theta minus sine square theta all over. The bottom is going to be square root of r squared times cosine square theta plus sine square theta. This is beautiful information. Why I say that this is beautiful information? Because cosine square theta plus sine square theta using Pythagorean trigonometric identity is equal to 1. So limit r approaching 0, you get r squared times cosine square theta minus sine square theta all over square root of r squared, which I'm going to just say r. Remember, r is approaching 0, so r is not equal to 0. So what I can do algebraic manipulation and say this is limit r going to 0, r times cosine square theta minus sine square theta. Now cosine square theta minus sine square theta is bounded. I know that these values cannot be infinity, so finite for sure, always. What does that give me? It gives me direct substitution. I can substitute r equal to 0. 0 times a finite number is going to be finite and it is going to be 0. And hence I have found the limit. So this is bypassing finding all this direction. Just recall that if you want to establish that a limit exists, you have to check uncountably infinitely many directions. What the polar transformation has given us, it has given us a way out to describe the same limit in two variables as a limit in only one variable. Remember, my limiting variable was only r. So I was doing calculus 1 limit by the polar substitution in a calculus 3 class, which made our life so much easier. And now I know the required limit for this function is 0. And this is going to be one of the techniques that we will be using heavily in order to assign limiting values. If it is possible, I'm not saying that this is always going to work. If it is possible, it is going to help us assign limiting values for several variable functions. And I have created a bunch of homework problems for you where you get to practice this concept. What other type of examples we have? Okay, pretty similar one. This time you have, I told you that x is r cosine theta, y is equal to r sine theta, and xy is approaching 0, 0. So I'm not going to show you the work why xy approaching 0, 0 enforces r to approach 0. What would rather do, we're going to execute the limit. So I'm going to rewrite this limit. This is going to be limit r approaching 0 as xy approaching 0 by the substitution r will approach 0. And I will get sine of square root of x squared, so r squared cosine square theta by the substitution plus r squared sine square theta. Well, as previously we have seen, this is just going to be r. So I will get to say that this is sine of square root of r squared times cosine square theta plus sine square theta. And cosine square theta plus sine square theta being equal to 1, I get to say that this is limit r approaching 0, sine of square root of r, and I'm just going to say that this is r. Since r approaches 0, this value after direct substitution will approach sine of 0. And what I'm going to get out of this thing, well, sine of 0 is 0, so your limiting value is 0. And that answers your question. So now you have found the limit of this function is equal to 0. Answers my question. All right. So this is a problem that is talking strictly about continuity. So this problem is telling you, you have this function sine x squared minus y squared over x squared minus y squared when x squared is not equal to y squared. If x squared is equal to y squared, then the value is 1. So talk about the continuity of this function. So it's a piecewise defined function of several variables. So remember your usual notion of continuity. I said that a function is continuous if limit x comma y approaches a point, say a comma b, of f of x comma y, a several variable function, equals the value of the function evaluated at the point a comma b. If that happens, then I say that the function is continuous at a comma b. So this is what I'm trying to check. First, I'm going to evaluate the limit. And what will be the limit? So I will say that limit x squared approaches y squared. I don't care which way they're approaching, but x squared should approach y squared. And I will evaluate the limit of the function sine of x squared minus y squared over x squared minus y squared. Why I am interested in this limit? Well, this is the only situation that you are wanting to know, as the rest of the points when x and y are not approaching each other, the bottom of this function are going to be well defined. If x and y are far away from each other, then the value is going to be a finite number on the bottom. The only situation when I'm going to be worried about is when the bottom is nearing 0. Remember, those are the points where we cannot do the direct substitution if the denominator is equal to 0. So I'm trying to avoid that situation. So it is continuous everywhere for sure, except when x squared and y squared are very close to each other. So I want to eliminate that situation as well. I already know this function is continuous everywhere on the plane when x squared and y squared are not close to each other. So what happens when they are getting close to each other? So we're trying to evaluate this limit. And by this point, you know that the substitution that generally is going to help us is the r cosine theta, r sine theta substitution. So what I will do, I will go ahead and try to do that. So I will say that let's substitute x equal to r cosine theta and y equal to r sine theta. And remember, this time you are not approaching 0. What you are doing, you are saying that x squared is approaching y squared. So find x squared. X squared is r squared cosine squared theta, and y squared is r squared sine squared theta. Well, what else? Then I get to say that x squared approaching y squared implies r squared cosine squared theta is approaching r squared sine squared theta. So I get to say that means r squared cosine squared theta minus r squared sine squared theta. So if I subtract r squared sine squared theta from both sides, I will get that to approach 0. Which means I get to say that r squared times cosine squared theta minus sine squared theta will approach 0. Let's see where we're going to use this information. Now come back to your limit. You're going to rewrite this limit as limit r squared cosine squared theta minus sine squared theta. That's what we have obtained, approaches 0. That is what it is to say x squared is approaching y squared. And the function becomes sine of, well, x squared minus y squared. Isn't that exactly what we have done here? So we'll go ahead and say that this is r squared cosine squared theta minus sine squared theta. Should put them inside parentheses. That's the top. And the bottom is just x squared minus y squared. So this is r squared cosine squared theta minus r squared sine squared theta. Now recall the calculus 1 limit formula, which was a very important limit formula. It said limit theta approaching 0, sine of theta over theta is equal to 1. And don't I have the exact same thing? Call r squared times cosine squared theta minus sine squared theta is your, say, alpha. This entire quantity is your alpha. So what do you have? You have limit alpha approaching 0. In the function, the top is sine of alpha and the bottom is alpha. And that's exactly matching with the limit formula that we have learned in calculus 1. So I know that this is going to be equal to 1. And hence, I found when x squared and y squared are close, pretty close to each other, the limiting value is 1. Now recall that the piecewise defined function also said when they are exactly equal to each other, so f of xy is equal to 1 if they are actually equal to each other. What does that say? It says that if they are not equal to each other, then I know the function is continuous. If x square and y square are not equal to each other, then I know that this function is a very well behaved function because the bottom is just not equal to 0. The problems are when x is becoming very close to y or x square is becoming very close to y. Well, I found that the limit is 1 in that situation, which agrees with the functional value when x square is equal to y square. So the functional value when x square is equal to y square equals the limiting value when x square is tending to become equal to y square. So what it does say, it says that the function is continuous even when x square is equal to y square. For all those points on the plane, when x square is equal to y square, your function is continuous there too, as the limiting value, x square approaching y square, becomes equal to the functional value when x square is actually equal to y square. Both of them are 1. So the function is continuous everywhere. Because otherwise, we have already seen that the function is continuous everywhere. So I go ahead and go say that the function is continuous everywhere on the entire two-dimensional Cartesian coordinate plane R2. And I hope this is going to help you do your homework problems on WebAssign. If you have any question, please let me know. And I'm going to stop our session today and come back tomorrow.